Swayam Prabha. Digital India. Educated India.
We have been discussing about the thermodynamics of solutions for the last 2 lectures. So today we are going to continue and discuss even further. So I started discussing about the ideal solutions. As you know, in the ideal solutions the heat of mixing or rather change of heat of mixing or change of enthalpy rather is 0, and that is a very ideal situation, and therefore it cannot be applied for real solutions, and that is why we need to modify this aspect, which we will discuss today in this lecture. Now before that, let me just tell you that we know that I discussed with you about few important aspects. One, which is of paramount importance, is the free energy change for a solution is in general is given by dG equal to STT plus phi dP plus summation of the chemical free energies of the system. That is actually summation of the chemical potential multiplied by the mole fractions of individual elements summed over from element 1 to element n. So this actually boils down to, if I integrate these equations, obviously I can get at, okay, let us do the first thing, at constant temperature and pressure or pressure and temperature, dt equal to dP equal to 0 or dt equal to 0, dP equal to 0, therefore is equal to summation of I 1 to n mu I dxi. So for a binary system, we can write down very simple. Binary system will have 2 components. Let us suppose it has mole fraction of A as xa, mole fraction of B as xb. So therefore this is equal to 1. So in a binary system we can write down this dg equal to mu I mu A dxa plus mu B dxb, and thus integrating this we can easily get G at constant temperature pressure is equal to mu A xa plus mu B xb. Okay. So now using these 3 things, one is this this is the fundamental equations at the top, equation number 1, equation number 2, as well as the conditions that xa plus xp equal to 1 in a binary system. So therefore dxa is equal to minus dxb. We can write down dxa plus dxp equal to 0, 1 is a constant. So therefore dxa is equal to minus dxp. We can actually use these 3 equations, or these 3 equations to arrive at that mu A and mu B can be easily derived as a tangent to the free energy curve, and this I leave it to you to derive it, because I have given you the equations. You can do at a part of homework in the course and derive. This is very simple, as you can see here. Simply you have to plug in these equations in the master equation, that is GPT equal to mu A plus xa plus mu B plus xp. You just do that, differentiate it, you will find out the mu A and mu B expressions, and mu A xp expressions, then you will find out they are given by the tangent to the curve. So tangent to the curve is basically, that is what we have been discussing. Suppose this is my free energy versus composition plot. This is x or xb, whatever you can define, the pure A end, pure B end. Now I will draw using a color chalk so that it has become very easy for you to follow. So suppose this is my free energy curve. Okay. And so that means this point is equal to mu A 0, this point equal to mu B 0, right. So if I want to derive the equilibrium condition, or the, sorry, rather not equilibrium condition, rather the mu A and mu B for the solutions, suppose this is equal to xb equal to xb1. Okay. So at this point what I do is I draw a tangent to the curve. Okay. This is what I was telling, and this tangent will, the equation easily will get from these derivations. The tangent will be extended toward the A end and the B end. So if I extend to the A end, I get mu A for xb1. Similarly, I get mu B for xb2. Sorry, xb1, not 2, because xb1 is the composition at which you are deriving. That is the way actually the tangent to curve rule applies, or it is getting applied. So for two phase mixture, as I told you in the last lecture, again I am doing it for your understanding. For two phase mixture, the same, suppose I have alpha phase, this is G alpha, okay, this is G, let me write down, otherwise, and this is suppose G of gamma, as we discussed. So, we have to find out the equilibrium conditions. We need to draw a common tangent between these two, okay, and this common tangent obviously is to both the curves, and that is why the phi energy, chemical potentials will be like this. Okay, chemical potential of mu B in the alpha is same as chemical potential in mu B in the gamma. Similarly, here on the A end, this point here, mu A alpha is equal to mu A beta, mu A gamma. So that you can clearly see that this is a fundamental aspects in the phase stability or phase equilibrium. If I have two or than three phases, the similar rule will apply, that we will see in eutectic phase diagrams or eutectic or eutectoid systems. We will apply the same rules. That is what I am discussing so much on these, I am spending so much time on these. Now upon knowing all these aspects, you must be you must have a fair amount of idea that these chemical potentials normally can be written like this. Chemical potentials of the phases can be written like this. This is graphical representations. So I can write down the chemical potentials for the binary system as mu A equal to GA0 plus RT log of XA, and mu B is GP0 plus RT log of XB. Okay, so that is the derived equations of the chemical potentials, but most of the cases we will not apply these equations algebraically, but we will apply the constructions, very simple constructions. Okay. So that is the recap from the last lecture. For the last 7-8 minutes I talked about it. Now let us move on to the aspects which I told you at the beginning, that most of the solutions in the real life are not ideal. So therefore delta H mix in the phi energy equations, delta H mix is not equal to 0. So therefore we have to find out a model which will allow us to calculate what is the delta H mix. So carry over on these aspects. Let us first draw a simple two dimensional lattice of atoms. Okay, this is two dimensional lattice of atoms, and let us suppose this is my B atom, so, and this is my A atom. Okay, let us put it white so that you can see it. So I do it for many. Okay, so these are all A atoms. So for your understanding, let me write at the top, this I call A atoms and this I call B atoms. So, if in a solid solution like this, I have atomically mixed atoms, some are A, some are B. So, I could clearly see if I draw the bonds, suppose these lines indicates type of bonds. These lines indicate the type of bonds. As you see, there are three types of bonds here. One is between A and A, other one is between A and B, and third one is between B and B. Okay, is there any BB bonds? Okay, let us make it. If there is no, okay, this is BB bond. So there are three types of bonds present in solid solutions. Now this approach which I am going to discuss in the next lecture also carry over is known as quasi chemical theory of solutions. Basic idea purpose is to find out expression for delta H mix. I have discussed to you too that delta G mix depends on two things. One is delta H mix minus G delta S mix, and delta X mix expression I have already derived. So for the ideal solutions we assume that delta H mix equal to 0. So this was the expression for delta G mix. But in the real solution delta H mix is not equal to 0. So basic purpose of this construction is to find out the delta H mix. The assumption is that in this theory that delta H mix is solely dependent upon the bond energies. That is the basic assumptions. It is also to some extent correct that the enthalpy of mixing or the even change of enthalpy of mixing is a direct functions of the bond energies. Now as you see in a binary solutions like this, when you have AA atoms, AA bonds, AB bonds and BB bonds, there are change of bond characteristics compared to pure A and pure BB than AB. So what is the change? Change is that if I assume the bond strength of AA suppose is like this, bond strength of BB to be like this, or epsilon BB, and bond strength of AB like that. So therefore the total bond energies, total bond energy of system is nothing but number of bonds AA, okay, AA bonds multiplied by the bond energies of AA plus number of bonds of BB multiplied by the bond energies of BB plus number of bonds of AB multiplied by the bond energies of AB. Correct. So if delta H mix is related to E, suppose this is E of solution minus E of A means pure A minus E of B, then we can clearly see this is nothing but, you can clearly write that this is EAES minus the bond and bond number of bonds from AA. Obviously this will be equal to, in a 1 mole this will be equal to Avogadro number N0 multiplied by A number of A bond energy, Avogadro number of atoms in a pure B multiplied by bond energies of pure B. That is what you will get. So we have to find out the expression for NA, NBB, NAB for the binary solutions. So this can be easily done by simply assuming that the number of bonds is nothing but proportional is proportional to the mole fractions of A or B or AB type of bonds. So suppose for Na I can write down if I have 1 mole of solid solutions, so then I have total number of atoms is Avogadro number A0 multiplied by the mole fractions of A multiplied by the coordination number of A. Obviously, a coordination number means A atom, suppose I have a B atom, it is surrounded by 1 A atoms, 2 A atom, 3 A atom and 4 A atom and then others, or let us assume this A atom, it is surrounded by 1 A atom, another A atom here and another B atom, B atom, B atom. So, okay, these nearest neighbors actually 1 to A and 3 B. So, in 2 dimensional scale it has a Z value of 5, but in 3D it will be more. So, that is why in general we put Z. So, that means what? This is the number of Avogadro number multiplied by the mole fractions of A multiplied by the Z is the coordination number for that. Similarly, NBB is nothing but N0 XB Z and NAB is nothing but N0 XAXB Z0, okay, Z. As you know, in a binary systems actually the this is what you will get, these are the probabilities of the systems. Now, if I do the complete mass, what I will find is like this, delta H mix, and that I leave it to you. Complete mass means you can rearrange the equations, you can plug in these values NAA, NBB, NAA and get the ES and then subtract this. What you will get, delta H mix is equal to sigma XA multiplied by XB, where sigma has a value of I think N0 Z into epsilon, which is, or rather let us write epsilon AB minus epsilon AA plus epsilon BB by 2, and this will be multiplied by 2, okay, normally, but many times this 2 is absorbed within A. So, thus I get an expression of delta H mix like this. This value is completely dependent upon the bond energy differences between AB bond and BB bonds. For an ideal solution, we assume that delta H mix is 0. For ideal solutions, we assume ideal solution, we assume delta H mix equal to 0. That means that the EAA minus half of EBB and EAB A plus EBB equal to 0. That means EAA is equal to EAB A plus BB divided by 2. So, the bond energy between AB is average sum of bond energies of A and BB. So, there is not much change of bond energies when the solution forms, but for the real solutions this is not true. Delta H mix is not equal to 0, that clearly tells you EAA AB is not equal to EAA plus EBB by 2. That will be the factor which will play a role in determining the actual value of omega, because omega is strongly dependent on this parameter. N0 is Avogadro number, that is fixed 6.023 to the power 10 to the power 3, and Z is a coordination number. So, if you have a FCC solution, Z is equal to 12, if it is a BC solution, Z is equal to 8. Otherwise, these are not changing much. What is going to change is that depending on type of atoms AB or A or BB energies, this value is going to be changed drastically, and then you can get different values of delta H mix. So, this is in a nutshell, although I have not discussed in details about the aspects, this is in a nutshell simple way you can derive delta H mix. Remember, the major assumption in deriving this is that we assume that the bond energies are actually contributing to the enthalpy of mixing. So, that means the enthalpy of mixing and the bond energies are actually equivalent, but there will be other aspects which will come to clear to you, other factors which contribute to delta H mix, those we will discuss in future whenever required. So, in a simplistic fashion I would say that we discuss first the case of ideal solutions and then we are going to discuss the real solutions. So now if I know delta H mix, I can write down delta G mix is equal to delta H mix minus T delta S mix. So that means delta G mix is equal to omega XA into XP plus R into T. Remember delta S mix is nothing but minus R XA ln XA plus XP ln XP. So therefore if I multiply it with minus T, that's become plus T. So this is what is actually the real expression of delta G mix for regular solution. Okay. For ideal solutions we know that delta G mix is ideal is nothing but RT XA ln XA plus XP ln XP, and I wrote these things in the last lecture as like this. So this is also correct, 1 minus XA ln X 1 minus XA or 1 minus X ln 1 minus X plus X ln X, because if we assume X as a mole fraction of B, then 1 minus X will be mole fraction of A as XA plus XP equal to 1. So this changeover from these to this is basically to facilitate your understanding that excuse me, that these two parameters, the mole fractions of A and XA and XP, must be visible separately so that you do not forget it. That is why I made a changeover. So now if I know this, I can simply calculate G of regular solution is nothing but G of G when I say step 1. So therefore I remember in the last class I have written step 1 plus delta G. So that means this is equal to XA G X 0 plus XP G A GB 0 plus this term, this is sigma XA plus XP plus RT XA log of XA plus XP log of XP. So finally we get an expression of G for regular solution. Now we will see how this G will depend upon temperature, depend upon sigma, depend upon XA or XP, correct. So for that we need to plot the data, and obviously we cannot change all the parameters together when you plot the data. So what we will see in the next when I make the plots, okay, what I am going to tell you, I will discuss in this lecture the case where sigma is equal less than 0. Remember, if sigma is less than equal to 0, what does it happen? Sigma is a strong function of, this is N0 Z multiplied by bond energies of AB minus bond energies of A plus BB by 2, and that we assume less than 0. This parameter cannot be making any change in the sign of this sigma. So therefore that means epsilon AB epsilon A plus BB by 2 is less than or equal to 0. That means AB is energy is less than or equal to average of the bond energies of A and BB. That means AAB bond is preferred because it has a lower bond energies, so they will prefer over A and BB bonds. So this is equivalent to saying that solutions will be promoted because solution will have more number of AB bonds than A and BB bonds. So therefore whenever sigma is equal to less than 0, you will clearly understand that G will be for the solutions will be lower than the individual mixtures. Okay, that is the thing. So now how do I plot? So obviously we can plot two cases here when sigma is equal to less than or equal to 0. One when the temperature is low, other one is the temperature is high, because as I said temperature is a factor, and in all these plots we are going to plot as a function of x b, right. So this is 0 this is minus, this is plus. So here I am going to plot T small. When T is small, small means they are room temperature or less than room temperature. And here I am going to plot again same thing G, okay, this is remember this is G, vertical axis is G regular solution, okay, as a function of xp when T is high. So there I will use different color chalks to facilitate you understand these things. First let us plot, obviously because sigma is less than 0 and we have seen that then this value sigma is negative, so this value is negative, okay. Sigma xa is positive, xp is positive, only thing sigma is negative, so therefore this value is negative, and we know that entropy term is always negative. So what will happen? Because of that delta H mix, I think it is better we plot delta G mix, that is better, then it is easy to follow. Let us change it to delta G, because delta G is also same as delta G, the only difference is that constant term is added. So this is for my delta H mix, okay, I write down delta H mix. So minus of T delta S mix will be also inverted parabola. Why this inverted parabola? I have told you, because if I expand this, it will looks like a parabola. This is already a parabola. This is because sigma into xa xb, that means xa into 1 minus xa, so therefore this is xa square, and that is why it is an inverted parabola, okay. Or if you are not understanding, I can write it down, sigma xa 1 minus xa, so I can write down sigma is xa minus xa square. So that means, or let us do it other way, because we are plotting xp, it will be similar, okay, x sigma 1 minus xb multiplied by xp, so that is equal to sigma xp minus xb square. So anything wherever you have a square term on the for the variable, that is a parabola, equation of parabola. So that means G delta G will be also looking the same kind of plot. So this is delta G mix. So that any value of xb, the solutions is perfect. That is what we discussed. When sigma is less than or equal to 0, for any value of xp, any value of the compositions on this pure A to pure B, solutions will be perfect, AB bond will be perfect. So similarly, for high temperatures, what is going to happen high temperature? Entropy term will increase further, that is what is going to happen, nothing else is going to change. So enthalpy will be slightly increasing because bond energies will slightly change, okay. Let me increase it a little further. So this is, here it is, okay, this is delta H mix. Now entropy will also increase further because the temperature term is there, and similarly your delta G term will increase. So this is T delta S mix and this is delta G mix. So whatever may be the value of sigma, value of xp, whether temperature, whether when sigma is less than 0, solution is always perfect. So we do not see any changes from ideal to regular when sigma is less than or equal to 0. For the sigma more than or equal to 0, we will discuss in the next class, since it will be changing when the value will be more than 0.